In this lesson, we will derive a few trigonometric identities that we can use and then use them to simplify some expressions that may involve some trigonometry. So essentially what we're doing is we're trying to write things in the simplest way we possibly can. So let's recall from the last unit. We have sine theta is y over r. We have cosine theta is x over r, and we have tan theta is y over x. And we have our reciprocal trig functions. So cosecant theta is r over y, secant theta is r over x, and cotan theta is x over y. So this gives rise to what we would call the reciprocal identities. And I'm going to show you this just for sine. So let's say we wanted to work out what is 1 over sine theta. So we want to know 1 over y over r. So that is equal to 1 divided by y over r. So see here, the order is important. We're taking 1 and we're dividing it by the result of this division. So we want to take 1 divided by y over r. This is equal to 1 times r over y, which is just r over y. So essentially what this is saying is if you're taking 1 over a fraction, that is just the reciprocal of that fraction. So 1 over something is the reciprocal of that thing if it is something that's already a fraction. So if we did the same thing, 1 over r over y, that should give us back y over r. So r over y and y over r are mutual reciprocals. So what we have is 1 over sine theta equals cosecant theta. And that means 1 over cosecant theta gives us sine theta. And all of these reciprocals are going to be mutual. Reciprocal goes both ways. So if something is a reciprocal of, so cosine theta, sorry, 1 over cosine theta, let's write these in the same way. 1 over cosine theta equals secant theta, and 1 over secant theta equals cosine theta. And we have the same thing for tan and cotan. So 1 over tan theta equals cotan theta, and 1 over cotan theta equals tan theta. So those identities we can use are our reciprocal identities. So now we have another identity that we like, okay? So the tan, and these sometimes we call the tan and cotan identities. And identities are different. So identities are things, they are defined. You can replace one with the other. They are actually identified as these things. So these are equivalent. There is absolutely no difference, not for whatever different values, etc. So the only thing you have to be careful about is sometimes they don't work at zeros. But generally these identities these are exactly the same thing. Okay. So tan and cotan identities. We have y over r over x over r. Okay, so what I'm doing is I'm just looking, what is, if I take, this is sine theta, and this is cosine theta. So what I'm going to do is I'm going to actually simplify this. So I get y over r divided by x over r. That's going to equal y over r times r over x. You notice here that these r's are going to cancel, so that gives me y over x. Well, what is y over x? That's actually equal to tan theta, which we know from last time. So we have now our tangent and cotangent identities from doing this y over r. And you notice if we did x over r divided by y over r, we'd get the same thing in reverse. So we can actually, instead of using our y, x, and r, we can write tan theta just as sine theta divided by cosine theta. And cotan theta, reciprocally, is cosine theta divided by sine theta. And now I'm going to tell you something that will probably relieve all of your mind as you have been watching this. You will be getting a formula sheet that has most of these formulas on it. I don't give you every single one because some of them you can derive using the other ones, but I will give you a list of your useful formulas. So generally all of the formulas that you're seeing are formulas that you'll get. So these are the first group. We have our reciprocal identities. We have our tan and cotan identities. Now we're going to look at a different kind of identity. Okay, so first we need to look at a little tiny bit of notation. Okay, if I want to take the sine of theta and then square it, I will be writing that. So sine theta squared, there's a notation for writing the y value of sine theta squared. And that is sine, we write it as sine squared theta. So we don't have to write those brackets all the time. So this is the same thing. Sine squared theta like that means sine times sine theta times sine theta. This is not the same, big not equal, as sine of theta squared. So this is where you square the angle, square x, your x value, your input. This is squaring right here. This is squaring your y, your output. Okay? So squaring input versus squaring output, just make sure you're clear that that little 2 next to the sign means you're squaring the output, so we don't have to write brackets all the time. Okay, so let's take a look at our favorite picture from last semester. We're just going to do it using this kind of theta. Okay, so we have theta. Okay, we have our y, we have our x, we have our r. Okay, so what does the Pythagorean theorem tell us? Well, we know that x squared plus y squared equals r squared. And you guys used this actually quite a bit last semester. Sorry, not last semester. Unit 6, chapter 6, which was not the last unit, but the unit before. So what I'm going to do to both sides is I'm actually going to flip these around. I'm going to put the y first for some weird reason. Don't ask me why. I'll tell you later. I'm going to write y squared. I'm going to divide everything by r squared. So y squared plus r squared plus x squared over r squared equals 1, because r squared divided by r squared is 1. So I have y squared over r squared plus x squared over r squared equals 1. Now I'm going to simplify this. So y over r squared plus x over r squared equals 1. And this gives rise to one of everybody's favorite. This is probably, if I had one identity I want you to know really, really well, it's going to be this one. Now we can notice that y over r is just sine theta and x over r is just cosine theta. So we have this formula now, sine squared of theta plus cosine squared of theta equals 1. And that is a really cool identity. And guess what? It is called the Pythagorean identity. And there are a couple of corollaries to that based on when we combine our Pythagorean identity with our, if you go back, we have our tan and cotan identities. We can get some identities that arise from this, or just different manipulations and ways to write the same thing. So let's write sine squared theta plus cosine squared theta equals 1 over here. So now what I'm going to do is I'm going to divide everything by cosine squared theta. I'm going to put the 1 over there. So if I divide everything by cos squared theta, and then I rewrite it using my reciprocal functions, sine squared theta over cos squared theta is just tan squared theta. Cos squared theta over cosine squared theta is 1. 1 over cosine, remember 1 over cosine is secant. So that gives us, because that's the reciprocal of cosine is secant, so this gives us secant squared theta. So tan squared theta plus 1 equals secant squared theta. And that is another Pythagorean identity. So now we know sine squared of theta plus cosine squared theta equals 1, which really we're all going to have memorized by the end of this video. Let's divide it by sine squared theta. Make something else a 1. And from this, we get 1. So sine squared theta divided by sine squared theta is 1. Cosine over sine gives us cotangent. So 1 plus cotangent squared of theta is going to give us cosecant squared of theta. So now we have even more identities that come from the Pythagorean theorem. Okay, so awesome identities. So what can we do? So let's see, let's just take a big look back. We've got our reciprocal identities. We've got our tan and cotan identities, and we've got our Pythagorean identity. So what can we do? The other thing we might want to notice, okay, is that if we have like 1 plus cosine theta, you remember how we had a conjugate for radicals. So if we have a 1 plus cosine theta, one thing we might be able to do in order to do some simplifying here, especially if we find it in a fraction, if we multiply by 1 minus cosine theta. So let's look here. 1 times 1 gives us 1, plus cos theta, minus cos theta, minus cosine squared theta. Cos squared theta. Okay, so this simplifies 1 plus cos theta minus cosine theta. That cancels, so I get 1 minus cosine squared theta. But wait a minute, Miss Eaton, 1 minus cosine squared theta. So if I go back and I look and I have sine squared theta plus cosine squared theta equals 1, doesn't that mean that 1 minus cosine squared theta is equal to sine squared theta? You guessed it. So this is equal to 1 minus, so this is equal to sine squared theta. Okay, so we can't just go around multiplying by conjugates because that would change an expression. But if we do have some kind of fraction, which you'll often see, and you're trying to simplify it, we can use that to multiply by the numerator and the denominator of a fraction. And that was actually what we used conjugates for when we were trying to rationalize denominators. Okay, let's simplify some things. Okay, so we're going to simplify. The first thing we need to know is expressions only have one side. So we're not allowed to do things to both sides of an expression. We're only allowed to manipulate things within the expression. However, we can use fractions can be multiplied by a over a. So you can multiply a fraction by the same thing, numerator and denominator, but you can't like multiply both sides or divide both sides to simplify an expression. Okay, so let's simplify. We have 2 over cotan theta plus cosine squared theta over cotan theta sine squared. Oh, sorry, cosine squared theta sine theta. So we want to simplify this. So what do I do? Well, I'm going to start by looking at my cotan theta. I know an identity for it. I could do 1 over tan theta, but I don't see any other tan thetas. I do see a sine theta. So I'm going to rewrite cotan theta. This is going to be 2 of cosine theta over sine theta plus cosine squared theta over cosine theta over sine theta. And I really recommend when you're doing these, you have your formula sheet on your desk next to you so you can go through and check and see what you can replace with what. Some of these problems require a relatively high amount of just playing around. Like you need to try something and see if it makes it simpler. And then if it doesn't make it simpler, sometimes you need to try something else. The more of these you try, the more you will be able to develop your instincts about what is likely to work and what is not likely to work in a given scenario. Okay, so over here, this is a sine over 1, so I can cancel that. Here, I've got 2 over cosine sine over sine theta. I'm just going to leave that for now. We'll deal with it. We're going to just end up dividing. And remember, dividing by this is going to give us the is like multiplying by the reciprocal. We'll deal with that in a minute. So one thing I notice here, this is now cosine squared theta over cosine theta. That actually looks like it might divide. Okay, because cosine squared theta is cosine theta times cosine theta. So let's rewrite all of this. So this is 2 sine theta over cosine theta. I'm dividing by a fraction. I'm multiplying by its reciprocal. This is 2 over 1 times sine over cosine. So this is going to be plus cosine squared theta divided by cosine theta. So just a little note, because this is a new notation. Remember, this is cosine theta times cosine theta over cosine theta. So we can cancel one of the cosine thetas. That leaves me with a cosine theta in the numerator. And now I remember sine theta over cosine theta is really just tan theta. So this is really equal to 2 tan theta plus cosine theta. And that looks a lot simpler than what we originally started with. Well, I also might have noticed that I could have used my common denominator to add these together way back up here. But generally it's considered without a denominator to be a bit simpler. Okay, but sometimes it's debatable what the simplest form is. And then we can absolutely have that, you know, if it's arguably one of them is simpler than the other, we can always have that discussion. Okay, let's try another example. And since I'm calling this example 2, why don't we just go back and call this example 1, which I realized I forgot to do in my own notes. I just got so excited about these trig identities that I just jumped right in and started simplifying them. So let's see, we're going to simplify again. All of the stuff here we're going to be mostly simplifying. So we have 2 tan theta. Okay. So we have 2 over cotan theta plus cosine squared theta over cotan theta sine squared theta. Okay. So I'm going to show you 2 pathways to solve this problem. And these problems can be a little bit fun or tricky because we're often trying to do them multiple ways. So here's one way to solve it. Okay. So I'm going to take cotan theta and I'm actually going to try to get a common denominator so I can add this stuff all together. So I'm going to make this 2 cotan theta, and I'm going to multiply top and bottom by sine squared theta to get that common denominator. Okay, so 2 sine squared theta cotan theta over sine squared theta. I can do that because that's just equal to 1. Plus cosine squared theta over cotangent theta sine squared theta. So now I can add these together. That gives me 2 sine squared theta plus cosine squared theta over cotan theta sine squared theta. Okay. So now what I can do is I might notice that this is equal to, well, let's try simplifying the denominator a little first. This is cotan theta, so it's 2 sine squared theta plus cosine squared theta. And I know that this is cosine theta over sine theta times sine theta times sine theta, because we're multiplying 2 sine squared theta. Cancel the sine thetas, and I get that this is 2, and instead of writing 2 sine squared theta up here, I'm just going to write sine squared theta plus sine squared theta. Why? Because I saw a cosine squared theta, and I know that my Pythagorean identity is going to allow that to be 1. Half the battle of this unit is getting so you start to see and recognize particular identities in problems. And like I said, you've got your sheet right next to you, so you're looking at these identities and saying, oh, there I see something that goes with an identity. So now I actually get, this is sine squared theta plus 1 over cosine theta sine theta. And so that is quite a bit different. That is quite a bit simpler. And I could simplify this, and this is where it's kind of debatable whether it's simpler in just sines and cosines or whether it's simpler with other stuff involved as well. So we've got now sine over sine, so that just gives me tan theta plus 1 over cosine theta times sine theta. So that's 1 over cosine theta is secant theta, and 1 over sine theta is cosecant theta. So it could be tan theta plus secant theta times cosecant theta. Okay. So now let's look at a different way to do the same problem. So that was method 1. So method 2, we could start trying to take it apart immediately. So we could go 2 over cosine theta over sine theta, plus here we have cosine squared theta over cosine theta over sine theta times sine squared theta. So I'm just going to cancel the squared with a sine here. Then we have a cosine, if you notice, that cancels right here.
Reminder that the Centennial Club Fair is happening right now in the library. Come down to see our clubs. Thank you.
Okay, so we're canceling here that sine squared theta with our cosine squared theta, and then we can cancel the cosine squared with the cosine. So this leaves us with a plus cosine theta over sine theta. And then here we have 2 sine theta over cosine theta. And so this gives us 2 tan theta plus cotan theta. Okay, and if we were to try to find a common denominator and add them together, we would be able to add that to there. So this one actually yields something that is possibly a tiny bit simpler than that one. So if we wanted to then try to separate out that denominator, we could potentially get something a bit simpler as well. Okay, next one we have okay, so simplifying with factoring. So one thing that I want you to see is that sometimes we're going to have to factor trig functions. So if we have something like sine theta cosine theta minus sine squared theta, we can factor out a sine theta. And this would be sine theta times cosine theta minus sine theta, which might enable us to cancel something if we're working with fractions. Another one is that we may even end up with things like a quadratic in sine theta. So sine squared theta minus 2 sine theta plus 1. So what I would do in this case is let sine theta equal a. So let's just make this simpler. So this is like a squared minus 2a plus 1. This factors pretty easily to a minus 1 times a minus 1. Okay, so this here can become sine theta minus 1 times sine theta minus 1. Or we could write it as sine theta minus 1 squared. So we can do the same kind of factoring with trig functions. We just have to take a broader view and see the whole sine thing is just, it's a variable. We factor it like another variable, and then we can replace it at the end.